In this video, we'll be discussing test sections and construction patterns. The purpose of a roller pattern. In this video, we will be discussing the construction of roller patterns. The purpose of a roller pattern is to determine the number of passes that will be required for our control strip and test section, and also to identify our peak density. The roller pattern also will help us compare our compactive effort versus the density that we achieve. The initial requirements for constructing a roller pattern include material information in Proctor data, testing the underlying subgrade, making sure that the required equipment is available and working properly, making sure the contractor has made all necessary adjustments, that the material being used is representative, and that the contractor is aware of any testing and no equipment traffic will be going over the area. To begin the construction of your roller pattern, you'll want to find a 75-foot section and allow 50 feet on either side to allow room for the roller to maneuver. You will then pick 3 locations spread out over the length of the section. Do not test in any areas of overlap, and do not test within 18 inches of an unsupported edge. At this point, you will ask your roller operator to make 2 passes over the section in vibratory mode. A pass is defined as crossing over the section with a roller in one direction. Therefore, 1 pass up and back over the same area is considered 2 passes. Make sure to position the gauge parallel with the roadway with the source end toward the direction of the paver. For all of our tests in our roller pattern, the gauge will be in backscatter position and in 15-second fast mode. Now that we've rolled over the area, we will determine density and moisture content at each of our testing sites, and we will record those on our TL53. We've done now 2 vibratory passes. We will record density and moisture readings at each of the stations. For our density, we will then add up those 3 tests and divide by 3 to find an average. We will do the same with our moisture. We will add them up, divide by 3 to find an average. Now that this is complete, we will make another 2 passes over the section in vibratory mode. Now we have 4 vibratory passes, and we've taken density and moisture readings at each of our 3 locations, and we will solve for the average for each. We will continue this process until we see that the density has increased by less than 1 pound per cubic foot, or if the mat starts to show any signs of distress or any cracking of an aggregate. Making sure to monitor the condition of the mat during the roller operation is vital. You'll want to keep an eye out for aggregate fracture, displacement or rutting, a pumping or springing effect, excessive segregation, or any tearing or other visible stress. For test number 3, you'll be doing another 2 vibratory passes, bringing us up to 6 vibratory passes. We will again take readings for density and moisture and solve for their averages. We'll then do the same thing for test 4 and continue this process looking for a change of less than 1 pound per cubic foot in our densities. Here, our density has gone up to 134.4 pounds per cubic foot. In test number 5, we are now up to 10 vibratory passes. We will again take readings for density and moisture and find the average for each. As you can see that between test number 4 and 5, the density increased by less than 1 pound per cubic foot. At this point, we will turn off the vibration and make 1 more static pass across the area. If the density increases by more than 1 pound per cubic foot, have the roller make 1 more pass. In test number 6, we've now done 10 vibratory and 1 static pass, which can also be written as 11S or 10V1S. We will determine density and moisture content at each of our testing sites and solve for averages. We want to make sure that the change from test 5 to test 6 is not more than 1.5 pounds per cubic foot. Here we have our roller pattern curve. On this curve, we will be plotting our ride densities from each of our tests, as well as the number of passes that got us to that density. At 2 vibratory passes, our density was around 125. At 4 vibratory passes, it had increased to almost 128. At 6 vibratory passes, we were just over 131 pounds per cubic foot. At 8 vibratory passes, we were at 134 pounds per cubic foot. And at 10 vibratory passes, we were right around 135 pounds per cubic foot. It is at this point that we changed over to 1 static pass, and we see that number decrease down to just shy of 134 pounds per cubic foot. We can connect all of these points with a line, and where we see the peak in the line is the number of passes that we'll be using for both our control strip and test section.